Okay, so now let's supplement part 2, which is a proof of proposition 7.2. And here we will do this by embedding into acceptable rejection sampling as in proposition 6.1. So the proof of prop 7.2. So what is the setup? U and V are independent and uniformly on 0, 1 distributed. Y is defined as square root of r squared minus 2 log v. So we want to do this by embedding into acceptable rejection sampling, and for this we need to know the pseudo-density of y. That's step 1. Compute the pseudo-density of y, and well, we do this by computing its density, and we are going to compute its density by computing a distribution function and by differentiating. Okay, so let's plug in everything. So we have r squared minus 2 log v square root less or equal than y, and also is the probability. And by construction, which I already said on the slides, this is greater or equal than r. So we have two cases. This probability is 0 if y is less or equal than r, and otherwise we have to take a deeper look. Okay, so let's now look at the interesting case, y greater than r, and here we will proceed by just rearranging the condition. So we have this expression, and now we are squaring everything. Well, squaring here is 1 to 1 because everything under the square root is positive. So we have r squared minus 2 log v less than y squared. And now we are rearrange further. So we are getting log v greater or equal than r squared minus y squared divided by 2. So don't forget to flip the greater or equal sign because we are dividing by minus 2. And now we are taking the exp. So we are getting the probability that v is greater or equal than x r squared minus y squared divided by 2. Okay, so what to do with this? First observation. Oh, that's the wrong pencil. The first observation, this is less than 1, since y is positive. Okay, and we have the probability of a uniformly on 0, 1 distributed variable. The probability of the event that this random variable is greater or equal than something which is smaller than 1. So how to proceed? Well, we have the density and we will use it. So let's now integrate over the density. Here's the indicator function, which is a density. And we have to integrate from this here unto infinity. And as I said, the lower bound is less than 1. So what we get is just 1, because the upper bound will reduce to 1, and minus the lower bound. So this is a distribution function, or at least the interesting part of it. So let's summarize. So it's 0 if y is less than r, or less or equal r, and it's 1 minus this exponential term here in the other case. Okay, so now we can differentiate to get the density of y. dy, and I was just wondering, so this should be g of y, of course. Okay, so we have 0 in this case, and for the second part, well, we are using the classical rules for differentiation. So differentiating the exp gives the exp, and if we differentiate minus y squared divided by 2, we just get a minus y, and using the chain rule and plugging everything together, we get this. Okay, so we have the density, and except one point, but one point doesn't matter, and which pseudo density we can use now. But the pseudo density is not uniquely defined because there's no normalizing constant, and in the following we will use this pseudo density here, g of y, and well, the indicator function, which we need because the density is 0 if y is less than r, and then we have y. We also cannot skip this because it's not a constant, but then we add this, so we divide by r, this will be useful, and x minus y squared divided by 2. So what we are doing is we don't use the density directly, but we multiply g hat density by exp minus r squared half divided by r. This will be extremely useful. Okay, so this is a pseudo density of y, and what is the pseudo density of our target distribution? So what's the target distribution? The target distribution is the tail variable xt, and since f of x, indicator function from r to infinity, e to the power minus x squared. And what we have nicely by construction, so it's one of these backdoor proofs, is that f of y is less or equal than g of y on r to infinity. So in fact we have that's a fraction of f and y and g of y on r infinity is actually divided by y. Okay, and now everything fits nicely together, so we can apply exception rejection. So proposition 6.1, and we have probability of xt less or equal than x is the same as the probability of y less than or equal than x under the condition u is less or equal than f of y divided by g of y, and as we have seen, the later expression simplifies to u less or equal than r divided by y, capital Y. Okay, and this is the proof of proposition 7.2, and this concludes the supplemental part.